So welcome back. Now we will try to solve numerical problems on superposition theorem. In the last lecture, we have seen the superposition theorem statement and also explanation, and we have done one simple problem of applying superposition theorem. But in this lecture, we will see a little bit complex circuit. So I hope that by the end of this lecture, we will be able to determine the individual source contributions using superposition theorem. So let us take a complex circuit. See, this is a complex circuit. You need to determine the voltage across 2 ohms resistor in the figure given above using superposition theorem. See, in this circuit, if you carefully see, you do have 3 sources. So, and you are supposed to determine the voltage across this 2 ohms resistor. Okay, so the circuit consists of 3 sources. One is a 10 volt voltage source, 20 volts voltage source, and 2 amperes current source are there. So let the voltage across this 2 ohms resistor be V if all the sources are acting, and if only individual source is acting, if only this is acting, let it be V1. If only this is acting, if only this is acting, V2 and V3. So my voltage when all the sources are acting simultaneously is equal to V1 plus V2 plus V3. So these are the contributions of individual sources to the actual voltage drop across the elements. Now we will take individual source and we will try to determine their contribution. So I will start with the first voltage source, 10 volts voltage source. So this is the circuit. I am considering only this voltage source, and the other two are being replaced by the internal resistances, which means current source is open circuited and voltage source is short circuited, which means I am trying to open this one and I am trying to short this one. See, this is the circuit. This is open circuited and this is short circuited. Only one voltage source is acting. So in that case, I will take the voltage drop is V1. So I am supposed to determine V1 now using these things. See, so this is my V1. This is my current source which is open circuited. This is my voltage source which is short circuited. So if I apply nodal analysis, this is 0, 0, 0. Here I do have 10 volts because there is a voltage source. Here I don't have anything, so I'll take it as VA. Here again I don't have anything, I'll take it as VB. And both are same, right? So this is VB itself. Now I'll try to apply KCL at each of these nodes and I'll employ nodal analysis. So when I write the equation for node A, it has 3 parts now. VA minus 10 by 10 plus VA minus 0 by 20 plus VA minus VB by 2. This is the first equation. If I try to solve it, this is LCM and this is the equation. You can do it on your own. Next thing is at node B. This is at node B. At node B also I do have 3 parts. This is the first part, VB minus VA by 2. And the second path, see, it is open circuited here, so no current will flow. So that's why I should take it as the path in this current is 0. The current in this path is 0. So that's why I have taken it as 0. And in the third path, there is a current. This is VB and the voltage here is 0 volts, right? VB minus 0 by 5. So when I try to solve this one, see, I should start with the home node and I should end with some node where potential is known or to be identified. So in this case, it was VB to VA minus 2 by 2. This is VB minus 0. Actually, there is an open circuit, so I shouldn't take it the current. So I should directly take it as 0. Third path, VB to the nearest node voltage is 0 by total resistance is 5. I have solved it and I have obtained this equation. So if I two equations are available now, if I solve them, this is my VA, this is my VB. Okay. So in that case, my voltage across this 2 ohms resistor. What is it is? This is VA, this was VB, right? So VA minus VB. I have obtained VA and VB, so VA minus VB, this is my voltage. Similarly, this is V1 due to the first source, 0.974. Now we have to do the same, repeat the same for the next 2 sources. So now considering only 20 volt source acting alone now. Only this source is acting, the remaining 2, this is to be open circuited, this is to be short circuited. See, it is short circuited. This is also open circuited. Now again, I'll take mesh analysis or nodal analysis. I prefer nodal analysis basically. So this is my circuit. So the bottom 0, 0, 0. If this is 0, then automatically this is 20 volts. This one I'll take it as VB, this one I'll take it as VA. Since this is 0, this is also 0. No voltage source available here. Okay. So now there are two nodes again, VA and VB. So at node A, there are three paths: VA minus 0 by 10, VA minus 0 by 20, VA minus VB by 2. Similarly, if you solve it, you will get 13 VA minus 10 VB. I am not going into solving the equations now. You do at home. At node B, see this is VB minus VA by 2. This is VB minus 0. Actually, I should take. But since it is open circuited, I am not considering. I am directly taking the current as 0. And the third path is VB minus the nearest. Here it is 20. Earlier we used it to consider up to here. But here there is a voltage source. So its voltage is 20. VB minus 20 by the resistance in this path, 5. So this is my equation. VB minus 20 by 5. So if you solve this, you will get this equation. 5 VA minus 7 VB. So if I solve this first equation and second equation, I will get VA and VB. So what is the voltage across this particular 2 ohms resistor? This was A, this was B. So VA minus VB, I will be getting minus 2.926 volts. And this is V2. Similarly, the third source, which is the 2 ampere source. In this case, both voltage sources are to be shorted, right? So this is the way how I short the things. So now there is a current. I can apply again nodal analysis. So the same 0, 0, 0. This is also 0. So this is VA and this is VB, right? So when this is VA and this is VB, if I apply KCL in these nodes, three paths, VA minus 0 by 10, VA minus 0 by 20 plus VA minus VB by 2. Similarly, when I go with this node, this is VB minus VA by 2. Okay, VA minus VB by 2. And this is VB minus 0 by 5. Okay. And see, actually there is a current already flowing in this circuit and it is flowing in opposite direction. So I am taking it as minus 2. And this is the equations. These are the equations. Now I do have two equations now. If I solve them, I will get VA and VB. So the voltage across 2 ohms resistor is, if I take this one as V3, this is minus 1.463, which means that each source is contributing to some amount of response in that primary element. And see, if the responses are V1, V2 and V3, see this is the first response due to first source, this is response to second source, response due to third source. So if I algebraically sum them, this is my final response. So voltage across 2 ohms resistor is minus 3.416 volts. Okay. I hope that now you are able to determine the individual source contributions using superposition theorem. And this is your voltage drop determination across this 1 kilo ohm resistor using superposition theorem. Okay. So practice them at home. Thank you. We'll meet again in the class tomorrow.